really, really cool. Okay. So those are some of the very cool sort of implications of supersymmetry. And once again, supersymmetry is kind of needed in order to unify some of these fundamental forces that we spoke about, pretty much all of them, actually, because the three non-gravitational ones needed, and string theory, which is a grand unification theory candidate for all of them, including, of course, gravitation, which is sort of neglected in particle physics, if you will. It's not that particle physicists are wanting to neglect gravitation, but they just seem to end up neglecting gravitation and does not explain gravitation within particle physics. Well, if you have a candidate theory such as superstring theory, that too requires supersymmetry. So this is why we actually spent some time talking about supersymmetry in the past as well. And with that, I will actually take your leave now. Thank you so much, everybody, for being here. In fact, I will not take your leave just a second because I will show you that picture I promised and maybe read some of these comments on my laptop, okay? So I'll scroll up and read your comments on the laptop to see if there's any questions, and I'll show you this table of particle physics, particles that we just now talked about, and give you the summary. Okay. So let me do that right here, right now. By the way, as we talk about supersymmetry, super partner particles, and Susy and super all of that, could you please do a super chat? That would be most amazing to keep this channel going and to support the efforts of this channel. That would be most amazing. Much appreciated. I'm going to turn the camera now to show you the particle physics summary here of all the particles. And I will be looking at your comments on my laptop as I scroll up so that I don't disturb the camera view here. And thank you so much, everybody, for being here and for all your questions, comments, thoughts, dreams, and wishes. Stay safe, take care, and I will rotate this and still hang around here for a bit, okay? There's my microwave. Okay. And here's the chickpea container that you were on. And there it is. Here's the elementary particles. Here's the leptons that we mentioned. For example, the electron is a type of lepton. Then we have in that same family, we have muons and taus. These are heavier than the electron and they decay much faster than the electron. So you might not encounter them in nature as easily. Then we have neutrinos. We have the electron neutrino, the muon neutrino, and the tau neutrino. These are also leptons, and these are in the same family. Oh my gosh, did someone do a super chat? Oh, thank you, Acacio. Let me thank you properly in just a second. Let me keep going for now. So in the family of leptons, we have electrons, muons, taus, electron neutrino, muon neutrino, and tau neutrino. So those are the leptons, of which the most common, of course, is electrons. And you probably are very familiar, but keep in mind that along with electrons in the lepton family, we also have muons and taus. These are heavier than the electron, but they also decay a lot faster than the electron, and so you might not see them out and about in nature too often. And then we actually have these very elusive particles that are also in the lepton family called neutrinos. There are three flavors of them: electron neutrino, muon neutrino, and tau neutrino. All kind of form the lepton family. Now, the electron, muon, and tau, of course, have charge. So because they have electric charge, we namely have quantum electrodynamics. Of course, they both have quantum effects as well as electromagnetism effects between them. And so we developed this thing called quantum electrodynamics to describe the interactions of electrons, muons, and taus, because these things have charge. The neutrinos right here, see in this little row right here, all these neutrinos, each of these getting this like nu symbol. The V looking symbol here is called the nu Greek letter. And see how these are all neutrinos, three different flavors of neutrinos. None of them actually have an electric charge. So they don't care about quantum electrodynamics because they don't interact with electromagnetic force. They actually interact with something called the weak nuclear force, which we also mentioned. Then coming to the quark family right here, this is the quarks family. See, these two rows of particles are the quark family of particles, and we have the up quark, the down quark, the charm quark, the strange quark, the top quark, and the